Good morning. My name is Mahyar Moghaddam from Renewable, and I'm gonna present our paper which develops the idea of realizing self-adapting Internet of Things architectures by modeling control loops and their interaction. The research was performed under a collaboration among Renewable, University Grenoble Alpes, and French electricity transmission network company called RTE. We all work on CPS4 EU H2020 project. The concept of self-adaptation using MAPK loop patterns was already presented in literature. While the interaction among the functional loops is well addressed by literature, the interaction among various levels of control needs to be investigated. So we propose a conceptual framework which especially deals with the interaction among the functional and autonomic control levels. The functional control loops let the system adaptation within the environment, and the autonomic control lets the system to be adapted based on its own situation and goal satisfaction. You see the framework in the left side of the slide, in which we have different kind of stakeholders that we highlight the role of developers and managers here. Developers set the adaptation goals and design the system architecture. The functional control, which takes advantage of MAPK loop, gathers the data from the environment, interprets such monitor data based on functional goals, builds actuation strategies, processes them, and sends the execution commands to actuators. You see also autonomic control component that lets the system monitor itself continuously and perform necessary adaptation to achieve the adaptation goal. It actually monitors the system situation and assesses both the system functionality and quality to update the knowledge base. So the autonomic control analyzes the data coming from architectural components, compares them with goals, and sets a proper adaptation strategy to be executed by architectural variant. So this component architectural variant changes the combination of components and connectors in the form of architectural adaptation. This adaptation leads to two different architectural patterns that for Internet of Things you see in centralized, distributed, and hierarchical architectural patterns here. The patterns characterize IoT systems based on their level of distribution and collaboration. In centralized pattern, you see only one functional controller is in charge of controlling the environment. The central controller can be local or remote, kind of cloud or local server or so. In distributed patterns, the processing is performed locally under a potential collaboration of controllers. And in hierarchical pattern, local and remote controllers interact to satisfy goals. In the following slides, I show how each pattern and their transition can impact the system code within our application, actually. So, as a use case, we considered modeling RTE company's transmission network in Melosho area. The network includes 35 substations connected by 30 lines with some constraints regarding current and voltage. The network consists of traditional power transmission system as well as wind farms which generate kind of green energy. Since the policy was to use traditional grid system for distributing both power plant and green energy instead of constructing new infrastructure because they are costly, the problem of high voltage and current might happen. So as you see here in this picture, if a strong wind blows and the generation in D becomes excessive, and so here an overload will happen on the transmission line between B and A. This overload makes the safety problem for people, of course, who pass under these lines. So the problem should be managed by activating the circuit breakers or limiting the windmills production and using batteries to save some electricity. All right. Before this research here, we observed that RTE was using a traditional PLC-based system, but we designed their architecture based on a new framework they are developing that's called NASA. The architecture that follows a hierarchical style comprises sensors, gateways, central processing elements, and actuators. The sensors monitor the voltage and current situation as well as the position of circuit breakers to be activated. The position of circuit breaker is sent to the local gateway on every event, and the current and voltage measurements are sent every second to the local gateway. So each substation has a gateway that is in collaboration with other gateways. The gateway can act as a central controller as well if needed. So the we have another component, a central control element that comprises a solver that implements the model predictive control to optimize a cost function to use levers such as batteries and generation limit values and so on. You see in the left side of the figure the actuators. So the actuators are circuit breakers that are the fastest mode to stop the current in a line that actually is located in every substation. The batteries can store the electricity for 25 seconds to give some time to wind farms to shut down. The dashboard also shows the operators, the situational controller, sensors, batteries, and generators. We modeled the architecture using the queuing networks. Queuing networks provide the performance indices of the modeled system. The three architectural patterns presented previously can be modeled here also. The computation and sense data is performed by the functional control element. Here is shown as FCE, while the composition of FCE is set by autonomy control elements shown as ACE. They both use make-k logic. I explained what each component of queuing networks mean in the case study queuing networks that you can see here actually. So here you see environmental data are sampled by sampling nodes that are in charge of specifying the sampling rate. Here you see two sampling nodes since our sensory sampling rates are different. We have two different kind of sensors. The sense nodes afterwards we have here represent, I'm actually starting from left to right. So the sense nodes represent various types of sensors which take as input a specific kind of sample data. In our case, we have voltage and current and the circuit breaker's position. We have ACE, the autonomy control element that is represented by class switch node and monitor the situation of functional control, that is FCE, analyzes its situation based on system goal and plans architectural adaptation execution in line with system goal. So the adaptation change the combination of functional controllers, right? Functional controller deals with three modes to be performed. That we have three modes actually. First is fast action mode in our case study, that's activating the circuit breakers only, for which the computation consumes a low CPU. So the low CPU is with mode 1. The second mode is normal mode, in which the prediction for 60-second horizon is calculated. This computation consumes medium CPU. And third one is enhanced forecasting mode, with of course a longer horizon and with a high consumption of CPU. So we have also the fork join node which split the sample data for different sensor and actuation sets. And the actuation plan is implemented by actuators to achieve the common goal. It's the same as our case study. This table shows our queuing network task types and the corresponding service times. As you can see, the last column, we have three kind of controllers combinations and link to their actually architectural patterns. So we have here a centralized pattern in which a central powerful controller is used. In collaboration pattern, the distributed gateways with lower processing capability collaborate. And in a hierarchical pattern, a combination of gateways and cloud is considered. Of course, the network delay and processing time of each method is different and impacts the performance of the system. We consider 21 different scenarios resulted from the architectural patterns combination and performed simulation. Based on the simulation, we have got some results. As you see in the figure, managing the fast action mode as mode 1 and the normal mode, that's mode 2 with centralized, and the enhanced forecasting mode, that's mode 3 with hierarchical architecture, minimizes the system response time. In addition, adapting the architecture from distributed means from mode 1 to centralized, that's mode 2, and hierarchical for mode 3 provides the same optimal response time. That's 1.66 seconds. So in other sets of simulation, this part of simulation I said is shown with blue bars. In other set of simulations, we consider using the more powerful computing resources that's in actually central control elements for RTE as distributed gateway. So we push the powerful processor close to the edge of networks. And the result was that we observed an improvement in response time in all pattern transition where the distributed pattern is involved. So we, according to these results, we proposed a couple of suggestions to RTA company. We suggest that it's better to redesign the company, actually area architecture and its adaptation policy to manage the normal mode with central pattern and enhanced forecasting mode with hierarchical pattern. And also we suggested to push the powerful functional control to the edge of the network in a distributed collaborative way. Our approach lets designing the architecture and its adaptation based on modes. It facilitates runtime specification of functional controllers. In our future work, we will consider other complementary quality criteria such as resiliency to make architectural design decision. We will also apply our approach to test other performance indices. Another improvement to be performed in future work is formalizing both the runtime pattern selection process and sampling rate setting. I will be happy to hear your suggestions and questions. Thank you.